So last time we kind of finished up talking about acids, bases, pH, pOH, H plus concentration, OH minus concentration. And we talked about it at the end there after the quiz about strong acids and strong bases. A reminder that if you have a strong acid, it is a strong electrolyte, which means it's going to 100% break apart in solution. So something like hydrochloric acid, which is a strong acid, will again break apart into H plus and Cl minus. And really for pH, in terms of an acid, the H plus is really what you want to know. And if you are given the molarity of the whole thing, you could use sort of stoichiometry to figure out the molarity of the H plus. And then you could go right into your pH equation there and solve for it. We could also do this for strong bases. Works the same way. They're going to 100% break apart in solution. And the difference, though, is we are not going to be looking at H plus here. We are going to be looking at OH minus. And it's the same sort of idea. If you know the molarity of the whole thing, you can use stoichiometry to figure out the molarity of the hydroxide. And that's important because, once again, it is hydroxide, so it will not allow you to calculate the pH directly, but you can calculate the pOH, which is minus the log of the OH minus concentration. And then you can kind of subtract 14 from it and get yourself the pH in that particular case. Now, a reminder that we saw sort of a list of 6 strong acids, which is a really good one to know. And again, a reminder that in terms of the acids, we are looking at hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydroiodic acid as your kind of big 6 strong acids. They will 100% break apart in solution, and you'll be able to get the H plus concentration from it. In terms of your strong bases, as we also talked about, those are pretty much going to be your kind of group 1 and group 2 on the periodic table. And again, those guys with hydroxide is typically going to make a lot of your strong bases, again, like lithium hydroxide, sodium hydroxide, calcium hydroxide. So as we talked about at the end there, sometimes you may just be given an actual strong acid or strong base, and you can use either the H plus or OH minus concentration to calculate the pH of the solution rather than just a generic H plus or OH minus. Yeah, I would say in most cases, unless it's otherwise sort of stated, most things are sort of considered 25 degrees Celsius, sort of almost like a standard temperature sort of value. But in the case of, regardless of the temperature, whatever your H plus concentration or OH minus concentration is at that point, would go into there. Technically, the KW that we saw earlier on, which is the equilibrium constant for water, that value of 1 times 10 to the minus 14 is specific for technically 25 degrees. And if it happens not to be 25 degrees, you may actually see a different value used there. But probably 99.9% of the time, that KW value, you're going to use it as that 1 times 10 to the minus 14. Other questions? Okay. So then, obviously, we now know, and we talked about how to handle strong acids or strong bases. But what do we do with weak acids or weak bases? And as I also mentioned last time, knowing those sort of 6 strong acids, by process of elimination, if it is not one of those 6, you can probably safely assume that it's going to be a weak acid. So how do we handle weak acids? Well, weak acids will set up an equilibrium. So that might give a hint as to how we could handle these. And we can write an equilibrium expression for this because it is a reversible reaction. It is the exact same type of equilibrium expression we've done all through our chapters here. We would take our products over our reactants, still normally no liquids or solids included. So this would give us, looking at this reaction here, by the way, this is a generic formula for a monoprotic acid. Monoprotic meaning it's got one hydrogen to give. And if you don't have a specific acid given to you, you use HA as a just generic sort of formula for a monoprotic acid. We'll take our products over our reactants. And since this is the equilibrium constant for a weak acid, I'm going to assume that's what the A on the bottom there means. So that is the Ka value. We could add it to our ever-growing list of K values. We got Kc, Kp, Kw. Now we got Ka to our big list of Ks. Clearly, this class is brought to you by the letter K. Yes. Now, when we look at a weak acid, it has a Ka value here. And the relationship between Ka and acid strength is this. As the Ka value increases, the weak acid strength increases as well. And that is still the basic idea of equilibrium constant. Because if I asked you if I have a large value of K, would I mainly have reactants or products at equilibrium? You would tell me. All right, let me ask that. If we have a large value of K at equilibrium, should I have reactants or products? Products, right? Because it's products over reactants. So when you have a larger value of Ka, you mainly have products. And what we have on the product side here is free H plus. And that's kind of important, right? Because as the concentration of H plus increases, pH decreases, right? And becomes more acidic. So that's why when we have a large value of Ka, it's considered a stronger weak acid. It's still a weak acid, but in comparison to other weak acids, a larger Ka value would indicate that that is a stronger weak acid. It is nowhere near as strong as a strong acid, like those 6 in the list there, like HCl, nitric acid, or anything like that. But again, in comparisons of weak acids. So would I have perhaps a Ka value for a strong acid like hydrochloric acid? I'll spit that out. Like hydrochloric acid. Should I have a Ka value for that? Can I? The answer is you cannot have a Ka value for a strong acid, and that is because something like hydrochloric acid is not going to set up an equilibrium. It is a one-way street, and it's all going to dump out on the product side. You'll have none of these guys left. There is nobody coming back the other way. So because strong acids do not set up the equilibrium, we do not see Ka values for them. The only one that you might ever see a Ka value for in a table is sulfuric acid because it's a diprotic acid. And the value for the first hydrogen just says large, which is not a very helpful number or anything like that. So you typically do not see Ka values for strong acids because they do not set it up in equilibrium. Also, another way to recognize whether or not you are dealing with a strong acid or a weak acid, if you see a Ka in the problem or you see a Ka in the table that relates to whatever acid you're dealing with, it's a sure bet weak acid. So again, that's another way you can very easily recognize that you are dealing with a weak acid. Any questions on that? So here's a table, and you have a similar one in your book. And again, you can see some of our Ka values here. There are also, as we'll talk about a little bit later on in this chapter, when you have polyprotic acids, which have more than one hydrogen to give, there are Ka values for each of the hydrogens to come off. Now, how do we solve these type of problems? Well, let me just go back here. Actually, we'll talk about that first. How do we solve weak acid problems? The good news is, or bad news, you choose. If it is a weak acid, it will set up an equilibrium. And as soon as you think about equilibrium and solving for something, that should also trigger for you some ice table situation happening. So we do use ice tables here to solve these type of problems. Is it very different than a normal sort of ice table? The answer is it's really not. We set up our ice table like we normally would. we would run for our initial concentrations. We would do our 0, 0, our minus x's, our plus x's, our m minus x, and our x and our x. We would do just like we normally do, which is we would go into the equilibrium expression and solve for x. But in this case, the slight difference that we do in these type of problems is what we're looking for. So typically, if you're doing something with a weak acid, you are most likely looking for the pH of that solution. And that means that when we typically solve for x, it does equal the H plus concentration in most cases. And we just take the additional step of putting it into our pH formula. So we do solve these like normal. May require a quadratic. Could try the assumption like we talked about in the previous chapter. Any of those things. I'll be honest with you, with weak acids and stuff like that, you probably are not going to see too many perfect squares or anything like that. It's probably going to be either an assumption or you got to kind of go quadratic to solve it. You won't probably get too many like perfect squares on each side in most cases. Any questions on that there? All right, so then why don't you try it there? Again, going to work the same way. We're just going to try to figure out the pH of the solution through the H plus. So here's the Ka value we'll use for the HF, 6.4 times 10 to the minus 4. We want to know what is the pH if we started with a 0.5 molar HF solution. So take a few moments there, calculate it up, see what you come up with. Okay, let's take a look, see how you're doing. So a couple of things we want to kind of think about when we see a problem like this. Hopefully you can recognize HF as an acid, and then you want to kind of think about what type of acid might this be. So one thing I definitely see in this problem, written over here in the corner, is I do see a Ka value. So as soon as I see the Ka value, that should indicate to you that this is a weak acid. You don't even have to question it. Again, strong acids won't have K values or Ka values. Once you recognize it as a weak acid, that also, again, should just point you in the ice table direction as to what you want to do. So the first thing we're going to do is just write the dissociation of this weak acid. And once again, it is your choice. If you do want to include the water, you can. I personally don't include the water, so I'm just going to show it breaking apart. And that's going to break apart into H plus and F minus. Once again, if you did include the water on the left-hand side, instead of H plus, you would get H3O plus. So same deal, doesn't really matter whichever way you want to kind of show it. This is going to give us a Ka expression for this weak acid of the H plus concentration times the F minus concentration divided by HF concentration. That's going to equal our 6.4 times 10 to the minus 4. At this point, it's really just an ice table type problem happening. And in this case, we're going to go with 0.5. This is again going to be 0 and 0, just like we did with regular sort of equilibrium problems. Clearly, there's nothing mentioned about what's on the right-hand side there. So again, it is safe to definitely assume that it's 0 to begin with. We're going to go through here, a little minus x plus x action there. Going to get us at equilibrium 0.5 minus x, x, and x in this case. Any questions on the ice table there? Like a normal equilibrium problem, at this point, we're going to put all that into our expression. And again, the goal here is to solve for x. So popping that in, that is going to give us x squared divided by 0.5 minus x equals 6.4 times 10 to the minus 4. Now, again, you want to think about ways to solve this, and maybe an assumption here might be a good idea because maybe you don't want to do the quadratic. Maybe you do want to do the quadratic. I don't know. But we can make the assumption here, like we talked about in the previous chapter, because again, the Ka value here is a small value. It is less than 1. So we can attempt the assumption here. Remember that you could only do the assumption if your K value is considered small, which is less than 1. So here I'm going to assume that x is equal to 0. Also a reminder that you can't get rid of all the x's or you got nothing to solve for. It is just the x's you're going to subtract it from a number or add. So we end up with something like this. We're going to multiply this to the other side, and then after I do that, I'm going to come back and take the square root of it. So I'm going to go 6.4 to the minus 4 times 0.5, and then I'm going to take the square root of it. And that is going to get me an x value of 0.0178. I'll call it 9 at this point. First off, any questions on that? Yeah.
We assume that x is 0 is
That is correct. So the assumption is based on the fact that the K value is considered a small value, which means when it reaches equilibrium, you should mainly have reactants, which means if it's going to mainly stay on the reactant side, not very much is going to go to the product side. So the change part or the X part should be negligible. And that's why we get rid of only really the X's that we're subtracting from a number because they actually have an initial concentration. That's also why we really don't get rid of these X's because they started at 0. So because they started at 0, whatever they make is going to be relatively significant. Plus, you would have nothing to solve for as well. Correct. So anything that would have an initial concentration, you could set the X to 0. So basically, anytime you have an X that's going to be subtracted from a number or even added to a number, those are the X's that you would get rid of. Yeah. Any pretty much X by itself, you got to kind of keep because it pretty much started with 0 in that case. Other questions? Now, the second really important part, right, that we talked about when you do make this assumption is you should always check the assumption and make sure that it is good because trust me, it will not always be good. So to check the assumption, we take the X value that we got, we divide it by what we were going to subtract it from, which is typically the initial concentration, and we times it by 100%. And if we do that in this particular case, I get an error. No, let's see where I get there. We end up with not that. I think about 3.6%, if I'm not mistaken. Pop that in one more time here. Bad calculator. Here we go. 0.5 times 100. Now remember that the rule that we are following for our assumption is the 5% rule, which means if it is less than 5%, it is all good. 3.6 is less than 5%. So the check here is good. Put a little happy face. That means we do not need to go back and solve it some other way. A reminder that if you do check it and the assumption is not good, you got to go back and do the quadratic. Yeah, probably in that case, in that situation. All right, so this X value is good, which means for our pH, that is really what we need. We can see that at equilibrium, the H plus concentration equals X, which would equal 0.01789 molar. Now we could go right into our pH. And that's some nice numbers. All right, so minus the log there, 0.01789. Going to get us a 1.75 on the rounded number there in terms of our pH. And that is acidic, so that's good. Right, I ended up with a basic pH here, probably not so good in this case. Any questions on that there? So again, a reminder, it is really important to make sure that you do check your assumption because again, may not always be correct. So if we were to do, for example, just to illustrate that point, if we were to do this exact same problem, but instead of the 0.5 molar concentration, we had 0.05 molar concentration. That means if I were to run through this problem, I essentially would do the exact same thing I did on the previous slide. Except obviously I have a different concentration here of 0.05 molar, which sounds very similar. We're going to go minus X plus X plus X, equilibrium 0.05 minus X, X, X. This will go into our Ka expression just like previously, x squared 0.05 minus x equals, what were we using there, 6.4, I think, 6.4 to the minus 4. 6.4 times 10 to the minus 4, obviously making our assumption and assuming x is equal to 0, we would end up with x squared 0.05 equals 6.4 times 10 to the minus 4. Once again, multiplying and square rooting, just like we did on the previous one. We will end up in this case, though, with a x value off of our assumption. Yeah, do want to do that. Of x is equal to 0.005656. Now, though, when we take our x value and check it, our 0.005656, and divide it by our original concentration, 0.05, and times it by 100%, we now hit approximately 11%, which means this is a bad assumption. And again, a reminder that you should definitely check it because it will not always work. We will talk about why this doesn't work in a little bit more detail later on in this chapter, but just to preview for it, the difference between the first concentration of 0.5 and this concentration of 0.05, that's a big fold difference, right? There's a big difference between those two. It's a lot more concentrated in the first one we started with than the second. So if you think about it like a pizza, if you have a whole brand new pizza and you take out one slice, not going to be a big deal, right? So you still have a whole pizza almost left over. But if you started with like 2 slices left that nobody wants to take because there's only 2 slices in the box, and you take one of the 2 slices, you just took half of what was originally there, right? And that's a much bigger difference, right? So it's not negligible anymore, rather than the first piece of pizza where there's still 10 outer pieces that can cover for you. So the concentration that you start with a weak acid or even a weak base, when you do those type of calculations, this starting concentration is really important as to whether or not, for example, that assumption may work or may not work. So it is really important to make sure you always do check it. Any questions on that? All right, so as we just saw there, we basically work these problems the exact same way as normal equilibrium problems. In most cases, we will ignore the autoionization of water. What that means is this: the assumption that we make in our problems in this class is that all of the H plus that's in that solution came from the acid, or all of the OH minus came from the base, and those are going to be the major contributors. Now, some books and some people, and you sometimes see it in like solution problems and stuff like that, sometimes they'll go, well, the H plus concentration that came from the acid is much less than the stagnant water concentration of H plus that was in that solution. So we'll just go with water's concentration of H plus. So we don't worry about water's contribution to H plus or water's contribution to OH minus in these type of problems. We again just assume that the acid or base that's there is the major contributor, and we calculate the pH based off of that. So again, if you sometimes see that, that is why some people will sometimes take that into consideration. Again, here, the only real difference is at the end, we're really just looking for that H plus concentration so that we could go into the pH equation at the end. All right, so why don't you give it a go here? We have a monoprotic acid with a concentration of 0.122 molar, has a Ka value of 5.7 times 10 to the minus 4. What is the pH here? So take a few moments there, calculate it up, see what you end up with. Monoprotic acid doesn't actually give us a formula of a specific acid. So again, in this situation, you could use that HA formula as just a generic formula for a monoprotic acid. One thing that we do know about this monoprotic acid is it does have a Ka value. So once again, that should tell us it is a weak acid. And because of that, that again should tell us ice table is the route that we need to go in this case. So we're just going to start with our dissociation of our weak acid. And once again, if you do want to put the water in, you can on the left, but I'm going to not and just show it breaking apart here into its ions. This is going to give us a Ka expression of our products, which is H plus and A minus divided by our HA. And that obviously equals our 5.7 times 10 to the minus 4. So we're going to start here like normal. We got initial concentration of the HA 0.122. Once again, we could assume 0 here for the others. Change going to be minus X plus X plus X. Again, going to get us at equilibrium here. 0.122 minus X, X, and X in this case. Any questions so far on the table here? All right, so just like we did before, we're going to take the equilibrium line, put it into our expression. That's going to get you x squared divided by 0.122 minus x equals our 5.7 times 10 to the minus 4. Again, this is a weak acid. We do see a small K value. You could assume x is equal to 0, and hopefully you did, and hopefully you also checked it to see that it is about a 6.8%, which means not so good if you did the assumption. So in this case, the assumption does not work. You do have to go back and solve it, in this case, quadratically. So we're going to go back and solve it here quadratic. We're going to multiply that to the other side. That's going to get us here x squared is equal to 0.000, one more zero, 6954 minus 5.7 times 10 to the minus 4x. Maybe I'll just write it underneath here. We'll go this way. Minus 5.7 times 10 to the minus 4x. We're going to bring everybody to the same side. And when we do that, that's going to give us our x squared plus 5.7 times 10 to the minus 4x minus 0.00006954, I believe, equals 0. So again, that's going to be our A, B, and C here to go into our quadratic. And that again is our b squared, our minus b, plus or minus our b squared minus 4ac. So going into that, we're going to go minus b here, which is minus 5.7 times 10 to the minus 4, plus or minus our square root. If you do the b squared minus 4ac on the inside, you will end up with 0.000278485. If you then square root that number, you will end up with 0.01669, all divided by 2 times A, which is 1, all divided by 2 in this case. Going our plus root here is going to get us an x value of 0.008, I think 059. Going our subtraction root, going to get you a number that's not going to be very good for us because clearly it is negative and we're interested in the H plus, which is X, and it cannot be negative, right? So clearly this is not going to be the right one. This then would be the correct X value for us. And for the pH, we could see that is essentially what we need to calculate it. So the pH in this case will equal minus the log of the H plus concentration, which is essentially our X value. Right? And that gets us negative log of 0.008059, going to yield us a 2.09 pH in this case. Any questions on that there? So again, another reminder that you should check your assumption, as it will not always be correct. In this case, you actually probably got a pretty close answer. If you didn't check your assumption, just rolled right through it, but it won't always be that way. So make sure you do check it. Any questions on that? Also an acidic pH, which is good because again, it's a weak acid, right? So again, if you're shooting some basic pHs at this point, definitely doing some type of the calculation wrong. All right, last one here. Calculate the H plus concentration. And we also do the pH as well of a 0.01 molar HCN solution, Ka value 6.2 times 10 to the minus 10. See what you come up with. We have an acid. We know it's a weak acid. So again, we're going to go through our normal sort of procedure here. We're going to write our dissociation of our weak acid, break it apart into H plus and Cn minus in this case, a little cyanide. Our Ka expression in this case going to be our products, our H plus, our Cn minus divided by our HCN. That is going to equal our Ka value 6.2 times 10 to the minus 10. Going to roll in with our initial concentration here of 0.01. Going to zero these guys. Minus x plus x and plus x. 0.01 minus x, x, and x. Again, like normal, we're going to go into our expression at this point. That's going to get us basically x squared on top, 0.01 minus x on the bottom, equaling our 6.2 times 10 to the minus 10. That definitely is a small value of k, so we could give the old assumption the college try. And if we do it in this case, that gets us x squared divided by 0.01 equals 6.2 times 10 to the minus 10. Once again, I'm going to multiply to the other side, and then after I multiply, I'm going to take the square root. And if I do that, that's 6.2 to the minus 10 times 0.01, going to give us 6.2 times 10 to the minus 12. Going to take the square root of that. Going to get us an x value here of 0.00000. Could have done scientific notation if I took chemistry. So we end up with this. We do want to check it in this case. We're going to divide it by our 0.01. We're going to times it by 100%. And I think in this case, we are going to be okay here for sure. And we're like at 0.02%. So the check here is good. That's 1, 2, 3, 4, 5, 6, I think. So our correct H plus concentration here would be that one right there, 2.5 times 10 to the minus 6. And once we have that, obviously, we could go into our pH. 2.5 times 10 to the minus 6. It's going to get us a pH in this case. Looks like a 5.60 in this case. Yeah. Any questions on that one there? So again, we've seen a couple where perhaps the assumption works, some where it doesn't work. A lot of times it does work. Again, if you don't want to do the assumption, you do not have to. You could just roll with the quadratic and go straight into it. But if the assumption works, it can definitely save you some time, obviously, than going through the quadratic. So it's probably beneficial to give it a go and hope for the best, but definitely make sure you check it. Any questions on weak acid type problems here? All right. Next thing we're going to talk about is percent ionization of an acid or even a base. And the percent ionization is the amount of ionized acid divided by the initial concentration. So we take the amount of H plus that's in there divided by the initial concentration and times it by 100%. The way that we calculate percent ionization is actually the exact same calculation we do to check our assumption. So when you check your assumption, you're actually calculating the percent ionization of that acid or base, and it's the exact same calculation. The H plus is our X value divided by the initial concentration times 100 here. Now, when you have a strong acid, as we talked about, it is going to be 100% ionized. And that's what you see here. Strong acid, 100% of it is ionized. Ionization, dissociated, those are all fancy words of saying it breaks completely apart into ions, basically, right? So that's basically what it's talking about. And how much H plus is coming off. If you're dealing with a base, it would be how much OH minus, for example, would be coming off. But when we have a weak acid, we could see, as I mentioned earlier with my pizza example, that the concentration of the acid does play a big role in whether or not you're actually having a lot of it coming off or not. So as I mentioned before, if you look kind of down here, let me just kind of redraw it up here a little bit. This is 0 and like 100% ionization. So what we see is with our weak acid, as the concentration increases, the percent ionization is relatively low. And that's why your assumptions work in that case, right? Again, when you have a larger starting concentration, if you lose a little, it's not that big of a deal, right? Compared to what you started with. That would be the example of the whole pizza, and you took one piece, right? You still have a good amount of the pizza still left. But as the concentration decreases, gets smaller, you can see the percent ionization gets much larger. And again, that would be the example. You have only 2 pieces of pizza left and you take one away. You just took 50% of what you started with by just removing one little piece, right? So again, the concentration there plays a really big role in terms of what you will see in terms of the ionization. So smaller the initial concentration, much more of it's going to be percent ionized, even if it's a smaller amount coming off, because you started with a smaller amount. Again, larger concentration, less of it coming out there in terms of its percent ionization. So you obviously can have a regular percent ionization type problem where you just kind of plug and chug into the percent ionization. You can also use percent ionization to help you calculate certain things. So let's take a look at this example here together. A solution is 8 molar formic acid, and it is 0.47% ionized. We want to actually know what is the Ka value of the formic acid. So the first thing that we do know about formic acid in this case is we are looking for a Ka value, which means it definitely is a weak acid, right? Because those, again, are the only acids that have Ka values associated with it. So if I were to sort of do this problem, I would just approach it like a regular old sort of weak acid problem, which means I'm going to start with my formic acid and I'm going to break it apart into some formate and some H plus in this case. And initially here, I do have 8 molar of the formic acid to start with, which was given to me here in the problem. I have none of this and none of this. We could do our ice table like normal, minus x plus x and plus x. This will come to equilibrium 8 minus x, x, and x. So if we were just sort of working this weak acid problem like normal, we would roll through this. We would also write our Ka expression, which would be the concentration of formate times H plus over the formic acid in this case. Now, normally what we would do at this point, right, is we would kind of throw everything in the equilibrium line into our expression, right, and solve for x. The problem is we don't know what the Ka value is. That's actually what we're looking for in this particular problem. So there has to be some other piece of information here that we could actually use to help us figure it out. And that other piece of information in this particular case is the percent ionization. So as we just saw in the previous slide, to calculate the percent ionization, that is the concentration of the free H plus in the solution divided by the initial concentration of the acid times 100%. Now, I have a lot of that information given to me in the problem. I know that it is 0.47% ionized. I know the initial concentration here of my acid. That's going to allow me to solve for the H plus concentration. So if I rearrange this and sort of solve for the H plus concentration, the H plus concentration will equal our percent ionization, 0.47%, times our initial concentration of 8 molar divided by 100%. And that is going to give us an H plus concentration here of 0.0376 molar in this case, right? First off, any question on that calculation there? So basically multiplied this to the other side, divided that to the other side, yeah, to get everybody over there. All right, why is that helpful? Well, if I go to my ice table, I should hopefully be able to see that when we reach equilibrium, the H plus concentration is equal to X. So by doing my percent ionization, I have now found the H plus concentration at equilibrium. And that's pretty good because that does equal X. And because it is that X, it is the same X that we find here. And it's also the same X that we find here, as they are all the same X's, right? They're all basically the same thing. So what we could use here is our percent ionization to sort of back calculate the H plus concentration that we have at equilibrium. And from that, we now have the X values for everybody. And now we could actually get the concentrations of everybody at equilibrium. So we know that the concentration of H plus at equilibrium is 0.0376 molar. We also see that the formate here at equilibrium is equal to X. So the concentration of HCOO minus is 0.0376. And now we can get our formic acid at equilibrium by solving for it. And our formic acid in this case would be 8 minus 0.0376. And again, that's basically 8 minus X is where we get that from. And we would have 8 minus 0.0376, going to get us a 7.9624 molar. We have now found everybody's equilibrium concentrations, and that is definitely going to allow us to calculate the equilibrium constant, because now all we have to do is pop it into our expression. So putting that into our Ka expression, we will have basically 0.0376 times 0.0376 divided by 7.9624. And that is going to get us here a equilibrium constant of 1.8 times 10 to the minus 4 in this case. Found my scientific notation. So this is again one aspect you can use percent ionization for, kind of back calculate. You could also obviously just straight up calculate percent ionization if you have the H plus and initial concentration. Any questions on that? Or you do an ice table and you solve for the H plus concentration, you could calculate the percent ionization from it as well. Any questions on percent ionization? So again, that is basically the check to our assumption calculation. Where we're really checking is the percent ionization. And as long as it's less basically than 5% ionized, it is a good situation. All right, let's talk a little bit about the other situation that happens, which is weak bases. So just like weak acids, we can have weak bases. And maybe not surprisingly enough, weak bases will also set up an equilibrium because they are weak electrolytes. Unlike the acid, where I do oftentimes just leave the water out of the dissociation, I would highly recommend for bases that you put it in, because that way you can visualize maybe what's happening, that the water is going to act as the acid and the NH3 is going to act as the base. And that is where we generate our hydroxide. So I would probably recommend putting that in. This will give us a Kb expression of products over reactants, and like normal, no water included here as it is a pure liquid in this particular case. And that is known as a Kb value. B, I'm assuming for base. So if you have a Kb value, you will have a weak base. Much like a Ka value, you will not find a KB value for a strong base because once again, it will not set up an equilibrium. So just like when you're dealing with a weak acid, if you see a KB value for somebody, you can probably safely assume that it is a weak base. And just like a Ka, as the KB value increases, so does the strength of the weak base. Once again, larger K value, more products. More products means you have more free hydroxide. That is basically your definition of what a base is, right? The ability to produce hydroxide. So again, it's a stronger weak base. Once again, these guys here that are weak bases are nowhere near as strong as like sodium hydroxide or potassium hydroxide or an actual strong base. These guys have to go find some water and do a little reaction. Again, a strong base just needs to go for a swim basically and break it apart. How do we solve weak base problems? We do it the exact same way as we do weak acids, and we do ice tables. Now, one of the biggest mistakes that people make when they do this is when I go through my normal ice table here and I solve for X, what does X equal in this case? It equals the hydroxide concentration, not the H plus concentration. So when you solve for X, that will equal the hydroxide concentration, which means you're probably going to be doing a little POH action first, and then you're going to get yourself over to the pH at that point. So that is a super, super common error that people make, is they're just automatically think X is always the H plus concentration. And clearly in this case, it would be the hydroxide concentration. The other seriously major problem people have is writing that formula, that equation. And a reminder that in most problems that you'll be given, you're just going to be given like the starting stuff, right? They're not going to give you an actual equation or anything like that. So if you don't know how to write that and you end up with H plus on the other side, you are going to be doing like an acid calculation when it should be a base calculation. So it is really important to make sure you know how to write that equation so it does not lead your calculation part astray along the way. But it again does work the exact same way. You can make your assumption, you could quadratic it, you'll solve for X. But again, the additional thing you have to do on these is you're going to go POH first and then to the pH at that point. Any questions on that there? All right. I think that's a good